Piping vibration, Quantitative Thermowell Likelihood of Failure or LOF Assessment, Analyzing Thermowell Performance for Safer Pipe Operations. This topic refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Overview of Thermowell LOF Assessment. The likelihood of failure, LOF, assessment for thermowells is a critical process in ensuring the reliability and safety of pipework systems. Thermowells are protective casings for temperature sensors inserted into process fluids, and their design must withstand dynamic forces such as vortex shedding and mechanical vibrations. This assessment focuses on evaluating the likelihood of thermowell failure due to resonance between its structural natural frequency and vortex excitation frequency. The concept of LOF is based on determining whether the thermowell design can operate safely under given conditions without excessive vibration or fatigue. The technical module introduces three primary thermowell geometries: straight, tapered, and stepped. Each geometry has unique characteristics influencing its stiffness, natural frequency, and susceptibility to excitation. The assessment methodology involves calculating the thermowell's fundamental natural frequency, predicting vortex excitation frequency, and applying modifiers based on pipe wall thickness. If the excitation frequency approaches or exceeds a critical threshold relative to the natural frequency, the thermowell may experience lock-on, leading to potential failure. Understanding these principles is essential for engineers to design thermowells that meet operational safety standards and minimize risks associated with dynamic fluid forces. Straight, tapered, and stepped thermowells. Thermowells come in three main geometries: straight, tapered, and stepped. Straight thermowells have a uniform diameter along their length, offering simplicity but potentially higher susceptibility to vortex-induced vibrations. Tapered thermowells gradually reduce in diameter from base to tip, improving stiffness and reducing vibration risk. Stepped thermowells feature distinct sections with varying diameters, balancing strength and flexibility. Each geometry affects the thermowell's natural frequency and dynamic response. For straight thermowells, the natural frequency is calculated using a formula involving Young's modulus, moment of inertia, and length. Tapered and stepped designs require more complex calculations incorporating diameter ratios and section lengths. These geometries are chosen based on process conditions, fluid velocity, and installation constraints. Proper selection ensures that the thermowell avoids resonance with vortex shedding frequencies, thereby reducing fatigue and failure risks. Engineers must consider these geometric factors during design to achieve optimal performance and compliance with safety standards. Structural natural frequency and pipe wall modifier. The structural natural frequency of a thermowell is a key parameter in LOF assessment. It represents the frequency at which the thermowell vibrates when excited. For straight thermowells, the formula involves Young's modulus, cross-sectional area, and length. Tapered and stepped thermowells require additional parameters such as diameter ratios and section lengths. The parent pipe wall thickness significantly influences this frequency because the thermowell is supported by the pipe connection. Thin-walled pipes provide less stiffness, reducing the natural frequency and increasing vibration risk. To account for this, a wall thickness modifier, FM, is applied. FM values vary by pipe schedule, with thicker pipes offering higher modifiers. For example, Schedule 160 pipes have FM values near 0.96, while thin pipes below Schedule 40 have FM values as low as 0.42. Adding welded gussets can further increase FM, enhancing support stiffness. This adjustment ensures accurate frequency prediction and helps determine whether the thermowell design is robust under operating conditions. Strohel number, vortex excitation frequency, and LOF scoring. Dynamic fluid forces acting on thermowells primarily arise from vortex shedding, which occurs when fluid flows past the thermowell, creating alternating vortices. The Strohel number, S, characterizes this phenomenon and is calculated using the Reynolds number and an empirical formula. Once S is known, the vortex excitation frequency, FV, can be determined using the equation FV equals S times V times char divided 1000, where V is fluid velocity and char is the characteristic Thermowell dimension. Comparing FV to the Thermowell's natural frequency, Fn, adjusted by the wall thickness modifier, Fm, establishes the LOF score. If FV exceeds 80% of Fn times Fm, LOF equals 1, indicating a high risk of failure and the need for redesign. If FV is below this threshold, LOF equals 0.29, signifying acceptable design. This quantitative approach provides engineers with a clear criterion for evaluating Thermowell safety under operational conditions, ensuring reliability and preventing catastrophic failures.